In this lecture, I'm going to discuss the concept of indeterminate forms. So before I start indeterminate forms, so let me recall the Cauchy-Munillo theorem. It says that suppose the functions f and g are continuous in the closed interval ab and differentiable in the open interval ab, and also the condition g dash of x must not be 0 throughout the interval open interval ab. So then there exists at least one point c belongs to the open interval ab such that f dash of c by g dash of c is equal to f of b minus f of a by g of b minus g of a. Cauchy's theorem, Munillo theorem, will be useful for determining the evaluation of the indeterminate forms. And what are the indeterminate forms? So, for example, consider sin x by x at x is equal to 0. So, that is 0 by 0 form, which cannot be find the value of sin x by x at x equal to 0. So, let us consider another example. X square minus 1 by x minus 1 at x is equal to 1. Again, it is a 0 by 0 form. 1 minus 1 0, that is a 1 minus 1 0, 0 by 0 form. And another example, 1 minus cos x by x at x is equal to 0. So cos 0 is 1, 1 minus 1, that is 0 by 0 form. At x equal to 0 for sin x by x, and x equal to 1 for x square minus 1 by x minus 1, and at x equal to 0 for the function 1 minus cos x by x cannot be defined. So here question arises, so what are the functions f and g tends to 0, and what happen the ratios f of x by g of x? So this is question arises. Now let us apply the limit for the function now. So limit as x tends to 0, so that is sin x by x, so that is equal to 1. Similarly, limit as x tends to 1 for this function x square minus 1 by x minus 1, so this can be written as limit as x approaches to 1. X square minus 1 can be written as x minus 1 into x plus 1 by x minus 1, get cancel, that is the values, limit values 2. So similarly, 1 minus cos x by x when x approaches to 0, so that value will be the 0. So here in the case of limiting, when you approach the limit as x approaches to 0, the function f of x and uh, g of x approaches to the 1 here. So similarly, x square minus 1 by x minus 1 so goes to 2 when x approaches to 1. Observe that at the values of x or the function at x equal to 0, that is 0 by 0 form, here again 0 by 0 form when x equal to 1, and at x equal to 0 for this function 0 by 0 form, but their limits is totally different. When x approaches to 0 for this function, your limit is 1, here 2, then here is 0. Let me define the what are the indeterminate expressions. Now indeterminate expressions may appear in different forms. that is 0 by 0 form, infinity by infinity form, 0 into infinity form, infinity minus infinity form, 0 to the power of 0 form, and infinity to the power of 0 form, and 1 power infinity form. So these are the different indeterminate expressions. So let us take a note here. So 0 power infinity, so that is equal to 0, it is not a indeterminate form. Similarly, infinity into infinity, so that is equal to infinity, which is not a indeterminate form. So infinity plus infinity, that is equal to infinity, which is not a indeterminate form. So infinity whole power infinity, again infinity only. So infinity power minus infinity, so that it can be written as 1 by infinity to the power of infinity. So the by that is equal to 1 by infinity, that is equal to 0. So these expressions are not indeterminate forms. So only the indeterminate forms are 0 by 0, infinity by infinity, 0 into infinity, infinity minus infinity, 0 to the power of 0, infinity to the power of 0, and 1 to the power of infinity. So we have a fundamental rule for determining the indeterminate forms. So now we'll discuss the what exactly the Elapsed rule. So now we'll move to the Elapsed rule. So we'll take a theorem statement. Let f and g be differentiable function on an open interval containing at x equal to a, and if f of a is equal to f of b is equal to 0, so then limit when x approaches to a, f of x by g of x is equal to f dash of a by g dash of a. So we'll move to the proof of the theorem. So by using the Cauchy-Munillo theorem, so we can prove this result. So let us move to the proof here. Suppose f dash of a and g dash of a exists, and g dash of a is not equal to 0, and f of a and g of a is equal to 0. So then we have limit as x approaches to a, f of x by g of x can be written as limit as x approaches to a, f of x minus f of a by g of x minus g of a, since f of a 0 and g of a 0 from the statement. So one can write this can be written as limit as x approaches to a, f of x minus f of a by g of x minus g of a. So this implies this is equal to limit as x approaches to a, f of x minus f of a by x minus a divided by g of x minus g of a by x minus a, here multiplied by x minus a. So this implies limit as x approaches to a, f of x minus f of a by x minus a divided by limit as x approaches to a, g of x minus g of a by x minus a. So this is the definition of derivative at x equal to a. So this can be written as f dash of a by g dash of a. So therefore you can write limit as x approaches to a for the function f of x and the g of x, ratio of the function f of x and g of x must be is equal to derivative of the function f at x equal to a, that is f dash of by g dash of a. Suppose if f dash of a and g dash of a is equal to 0, if it is 0 by 0 form, then again we can extend the Elapsed rule. Limit as x tends to a f of x by g of x, so can be written as f double dash of a by g double dash of a. So provided g double dash of a is not equal to 0. Suppose if f double dash of a is equal to g double dash of a is equal to 0, again you have to use the Elapsed rule. Then limit as x approaches to a f of x by g of x can be written as f triple dash of a by g triple dash of a, provided g triple dash of a is not equal to 0. Again, if f triple dash of a and g triple dash of a is equal to 0, again you can apply the Elapsed rule. We can continue the Elapsed rule. So since we get a finite value of the ratio of the function f of x and g of x. Now to the problem. Evaluate limit as x approaches to 0 of the function 3x minus sin x by x. So by using Elapsed rule, so we can evaluate this function when x approaches to 0. So we have limit as x approaches to 0, the function 3x minus sin x by x. So here you can observe that when x equal to 0, 3 into 0 and sin 0 0, that is 0 by 0, since this is f of x by g of x, f of s and f of 0 and g of 0, that is equal to 0. So that is a 0 by 0 form. So now you can apply the Petal rule. So now limit as x approaches to 0, function numerator function 3x minus sin x by x, that can be written as, so limit as x approaches to 0, d by dx of numerator 3x minus sin x divided by d by dx of x here. Differentiate numerator and differentiate denominator separately. So limit as x approaches to 0, so differentiation of the numerators, that is 3 minus cos x. In the denominator we have differentiation of x is 1. Now let us apply the limits now. So 3 minus when cos 0 is 1 by 1, so that is 2 by 1 will get 2. L'Hopital rule can be written in the another way also, in the stronger form. Suppose f of a is equal to g of a is 0 and f and g are differentiable, and an open interval containing x is equal to a, g dash of a is not equal to 0. If x is not equal to a, then limit as x tends to a f of x by g of x, so that is equal to limit as extends to a f dash of x by g dash of x. Derivative of the function f dash of x and g dash of x separately in x approaches to a is same as limit as x approaches to a of the function f of x by g of x. So this is stronger form of the Elapsed rule. So by using this result we can solve the problems, we can evaluate the indeterminate expressions. Now let us move to the problem. Evaluate limit as x approaches to 0, x minus sin x by x cube. So now we have moved to solution. Limit as x approaches to 0, x minus sin x by x cube. When x is equal to 0, so 0 minus sin 0 0, 0 by 0 form. Here we can observe that f of 0 is 0, that is equal to g of 0. So is a 0 by 0 form. Now let us apply the Elapsed rule. So limit as x tends to 0, the function x minus sin x by x cube. This is f of x and this is g of x is x cube. So this can be written as by using stronger form of Elapsed rule. X approaches to 0. So x minus sin x differentiation 1 minus cos x by x cube differentiation 3x square. So now let us apply the put x equal to 0. So cos 0 is 1. When x equal to 0, cos 0 is 1. That is again 0 by 0 form. So 1 minus cos x and 3x square are 0 when x is equal to 0. Again applying the Elapsed rule. So limit as x approaches to 0, 1 minus cos x differentiation 1 differentiation 0 minus cos x differentiation minus sin x by 3x square differentiation 6x. So now put x equal to 0 for the numerator and denominator. Again we have a 0 by 0 form. Let us apply once again the Elapsed rule. So this can be written as limit as x approaches to 0, sin x differentiation cos x by 6x differentiation 6. So when x is equal to 0, cos 0 is 1 by 6. The limit value is 6, 1 by 6 when x approaches to 0 for the function x minus sin x by x cube. Problem, evaluate limit as x approaches to 0 of the function square root of 1 plus x by x minus 1 minus x by 2 by x square. So these are the form f of x by g of x. So when put x equal to 0 for the function 1 minus 1 0, then minus 0 0 by 2 0, so that is 0 by 0 form. Now we apply Petal rule. So now limit as x approaches to 0, root of 1 plus x minus 1 minus x by 2 divided by x square. So differentiate numerator with respect to x. So that is 1 by 2 root of 1 plus x. So then 1 plus x differentiation 1 minus 0 minus 1 by 2 divided by differentiate denominator, that is 2x. So now take x equal to 0, that is 1 by 2 minus 1 by 2 by 0, again 0 by 0 form. So again let us apply the Elapsed rule. So this is equal to limit as x approaches to 0, 1 by 2 into differentiation of 1 by square root of 1 plus x, that can be written as minus 1 by 2 into 1 plus x minus of minus 1 minus 3 by 2 into differentiation 1 plus x is 1, so minus 0 divided by So differentiation of denominator is 2. So now we take the x is equal to 0 here. So 1 by 2 to minus 1 by 2, that is minus 1 by 4. Between x is 0, that is 1 divided by 2. So this is equal to minus 1 by 8. So this is the limit value when x approaches to 0 for the function. Let us consider another example. Evaluate limit as x approaches to 0 of the function 1 minus cos x by x plus x square. So when take x equal to 0, that is equal to 1 minus cos 0 is 1, that is 1 minus 1 is 0 by 0 form. So where f of x equal to 1 minus cos x and g of x is x plus x square. If it is 0 by 0 form, you can apply the Elapsed rule. So that is equal to limit as x tends to approach. So differentiation of numerator 1 differentiation 0 minus of minus plus sin x divided by x differentiation 1 plus x co-differentiation 2x. So now let us apply the limit when x is equal to 0, sin 0, that is 0, when by 1 plus 0, that is equal to 0. So 0 is a finite value and itself is limit value. If it is not 0 by 0 for us, then we can stop the Elapsed rule. So 0 itself is a limit of the function when x approaches to 0. So let us take another example. Evaluate limit as x approaches to 0 of the function 1 minus cos x by x square. So when x equal to 0, again it is 0 by 0 form. So where f of x is equal to 1 minus cos x and g of x equal to x square. So now let us apply the Elapsed rule. Limit as x approaches to 0, 1 minus cos x by x square can be written as limit as x approaches to 0. Differentiate numerator 1 minus cos x differentiation. So that is sin x by x square differentiation 2x. When x is equal to 0, again it is a 0 by 0 form. So let us apply once again the Elapsed rule. Limit as x approaches to 0, sin x differentiation cos x by 2x differentiation 2. So when x is equal to 0, that is 1 by 2. So 1 by 2 is the limit value of the function 1 minus cos x by x square when x approaches to 0. So let us take another example. Evaluate limit as x approaches to pi by 4 of the function sin x minus cos x by x minus pi by 4. So when x equal to pi by 4, function value, that is sin pi by 4 is 1 by root 2 minus cos pi by 4 1 by root 2 by when x equal to pi by 4, 0 pi by 4 minus pi by 4, that is 0, again it is 0 by 0 form. Now let us apply the Elapsed rule. So limit as x approaches to pi by 4 of the function sin x minus cos x by x minus pi by, where f of x is sin x minus cos x and g of x is x minus pi by 4. Now let us apply the Elapsed rule. Limit as x approaches to pi by 4, sin x differentiation cos x and cos x differentiation minus sin x, that is plus sin x by x minus pi by 4 differentiation is 1. When x equal to pi by 4, cos pi by 4 is 1 by root 2 plus 1 by root 2 by 1. So this is the finite value. So let us take LCM. Root 2 is the LCM. 1 plus 1, that is root 2. 2 by root 2, that is equal to value is root 2. So root 2 is the limit of the function, given function, when x approaches to pi by 4. Let us consider another example. So limit as theta tends to phi for the function sin theta by pi minus theta. When theta is equal to pi, so sin pi is 0. When theta is pi, pi minus pi is 0. Again it is a 0 by 0 form. let us apply the L'Hopital rule. So that is limit as theta approaches to pi of the function sin theta by pi minus theta can be written as, so limit as theta approaches to pi, differentiate numerator sin theta differentiation, that is cos theta by pi minus theta different respect to theta, that is minus pi. So let us apply the theta is equal to pi, cos pi is minus 1 by minus 1, that is equal to 1. So limit is 1 for the function sin theta by pi minus theta when theta approaches to